There appears to be a critical gap in our understanding of the universe, as cosmology is approaching a standoff over one of its most fundamental questions. How fast is the universe expanding? For more than a decade, two distinct methods of measurement have been at odds. Observations of the current universe often show the rate of expansion, known as the Hubble constant, to be roughly 9% faster than what predictions based on early universe data suggest. Scientists had hoped that the James Webb Space Telescope, the most advanced telescope ever constructed, would help resolve this conflict. However, it has, in fact, deepened the mystery. The James Webb observations have made the discrepancy even more precise, presenting a challenge to the established model of cosmology. This has opened up a debate on the need for new physics to either modify or even replace the 40-year-old theory that currently guides our understanding of the cosmos. What we are now confronting is a profound and intriguing possibility: that there may be something about the universe we have yet to fully comprehend. Join us as we explore how James Webb's ultra-deep images may have confirmed that something is seriously amiss with our current interpretation of the universe. Our understanding of the universe begins with the Big Bang, the explosive event that created energy, mass, and space, all within an incredibly brief moment. This was followed by the formation of a young universe, a roiling plasma of matter and antimatter particles that briefly coexisted. These particles should have annihilated one another completely, but scientists believe that some unknown imbalance between matter and antimatter allowed more matter to be created, preventing the universe from collapsing in on itself. Gravity began to pull this plasma together, heating and compressing it. As sound waves, called baryon-acoustic oscillations, traveled at just over half the speed of light, they created ripples across the matter. At the same time, the high energy density of the early universe's compressed content caused space-time itself to stretch, pulling some of this matter away from the intense heat. As the universe expanded, ordinary matter, which interacts with light, condensed around invisible dark matter to form the first galaxies, linked together by an immense cosmic web. Initially, as the universe continued to expand, the energy density dropped, and thus the rate of expansion slowed. However, about 5 billion years ago, a mysterious force known as dark energy caused the universe to accelerate in its expansion once again. The most widely accepted explanation for dark energy is that it is a form of cosmological constant, an inflationary energy that remains uniform across space and time, woven into the fabric of space-time itself. Einstein referred to this concept as lambda in his theory of general relativity. As the universe grew, the overall density of matter decreased, while the density of dark energy remained constant, gradually becoming the dominant force driving the expansion. The energy densities of ordinary matter, dark energy, and light energy collectively set the upper limit on the universe's expansion speed. These ingredients also form the basis of the lambda-cold dark matter, lambda CDM, model of cosmology, which predicts both the universe's expansion and its eventual end through a heat-death scenario known as the Big Freeze. While many predictions based on this model have been validated, problems have emerged. One major issue is that, despite extensive observation, we still don't know what dark matter or dark energy actually are. According to Ofer Lahov, a professor of astronomy at University College London and a member of the team studying dark energy, most cosmologists agree that the universe's current composition consists of 5% ordinary matter, 25% cold dark matter, and 70% dark energy. The troubling reality is that we have no idea what the latter two components are. Even more problematic is the so-called Hubble tension, where different methods of measuring the universe's expansion rate yield conflicting results. Depending on the technique used, measurements suggest the universe is expanding at different speeds. This discrepancy has been dubbed the Hubble strain. Methods that focus on the early universe show it expanding much faster than the lambda CDM model predicts. These techniques have been extensively reviewed and validated through numerous observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team behind the new James Webb measurement, stated, the only explanation he can offer for this discrepancy is that the model we use to explain the universe might be missing something fundamental. To measure the rate of expansion, astronomers typically rely on a few different methods. The first involves studying the cosmic microwave background, CMB, the leftover radiation from the universe's first light, emitted just 380,000 years after the Big Bang. This radiation can be detected across the entire sky, and measurements from the European Space Agency's Planck satellite, which operated from 2009 to 2013, showed an extremely precise Hubble constant of around 67 kilometers per second per megaparsec, (mpc). A megaparsec is equivalent to about 3.26 million light-years. This means that if a galaxy is 1 megaparsec away from us, it will be receding at 67 kilometers per second. At a distance of 20 megaparsecs, that speed increases to 1,340 kilometers per second, and it continues to increase exponentially as the distance grows. The second method involves studying Cepheid variables, a type of star that pulsates in a regular cycle, with a duration of its pulse linked to its luminosity. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid was, the slower it would pulse, which allowed astronomers to determine the star's absolute luminosity. By comparing this to the apparent brightness of a Cepheid, they can estimate its distance, and from there, determine the expansion rate of the universe. The superlight axion, a theoretical subatomic particle, is gaining attention as a potential answer to the mystery of dark matter. It's believed to be related to primordial black holes left over from the Big Bang, yet despite decades of research, no Earth-based experiment has detected any evidence of dark matter. This raises the possibility that our understanding of matter might not need adjustment, but rather our theories of gravity. It's also possible that dark matter is not a single substance but a complex form of matter, similar to the various atomic structures we see around us. The universe could be full of dark stars, planets, and even life forms. Time itself is a tricky concept, as American physicist John Wheeler famously said, "For times, existence ceases. Everything happens at once. The flow of time as we perceive it may not be as straightforward as we think. Time does not flow independently. For something to stream, it must flow relative to something else, just as a river flows along its banks." This idea suggests that time is likely a mental construct, created by our brains to make sense of the constant information we receive. Additionally, while we believe in a shared past, present, and future, relativity tells us that time isn't the same for everyone. Depending on how fast someone is moving or the strength of the gravity they experience, their perception of time differs from ours. These effects, though noticeable at speeds close to the speed of light or near strong gravitational fields, are not evident in daily life. As Einstein wrote after the death of his friend Michel Besso, "Now he has departed from this strange world a little ahead of me." This reflects the fact that time itself, as we perceive it, is simply an illusion. Dark energy, discovered by astrophysicists in 1998, is a mysterious force responsible for the accelerated expansion of the universe. Despite being invisible and occupying space, it makes up roughly 23% of the universe's mass energy. Researchers initially thought that gravity was the only force affecting cosmic expansion, but the discovery that this expansion is accelerating led to the need for a new substance: dark energy. One possibility is that dark energy arises from quantum fluctuations in the vacuum, but quantum theory predicts a much greater energy density than what has been observed, leading to a significant discrepancy in our understanding of the universe. Perhaps the solution will come when we manage to reconcile quantum mechanics with Einstein's theory of gravity. In the meantime, space missions such as the Dark Matter Tracker, launched in 2023, may offer crucial insights into how dark energy behaves over time and bring us closer to solving this great scientific mystery. The question of why we haven't detected signs of extraterrestrial life has puzzled scientists for decades. In 1950, physicist Enrico Fermi famously asked, "Where is everybody?" during a lunch at the Los Alamos lab in New Mexico. This question has since been explored by physicists like Michael Hart and Frank J. Tipler, who theorized that extraterrestrial civilizations should be spreading throughout our galaxy. They proposed that self-replicating machines, if built by alien civilizations, could easily colonize the galaxy by using resources from each star system they visit. However, despite the vastness of the Milky Way, we have yet to encounter evidence of extraterrestrial life. Numerous explanations for this paradox have been suggested, but no consensus has been reached, leaving it one of the greatest mysteries in science. As Douglas Adams aptly put it in The Hitchhiker's Guide to the Galaxy, "Space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. The discovery of Cepheid variable stars as standard candles for measuring cosmic distances was a groundbreaking revelation. It allowed astronomers to use their fluctuating brightness to map out the vast scale of the universe. By observing the pulsations of these stars, scientists could develop a cosmic distance ladder, with each step taking them further into the universe's past. The first rung of this ladder is established by measuring nearby Cepheids and cross-checking their distances with their pulsation periods. As astronomers move further along, they use these readings to calculate the distances to stars and supernovae. By studying how the light from these objects has been redshifted, they can determine how fast the universe is expanding, giving them a precise measurement of the Hubble constant. In 2019, researchers led by Rees used the Hubble Space Telescope to study one of the nearest galaxies, contributing to our understanding of this cosmic expansion. According to the Standard Model of Cosmology, the universe was once a vacuum with a high energy density and intense gravity, causing rapid expansion. This inflationary period eventually cooled down, allowing matter to form and creating the Big Bang, which set the universe on its current trajectory. The idea that such a massive energy vacuum could spontaneously produce matter may seem impossible, but the laws of quantum physics support the notion that something can emerge from nothing. One of the major unsolved mysteries of cosmology is the origin of the laws of physics themselves. In 1980, German mathematician Emmy Noether proposed that the fundamental laws of physics result from deeper symmetries of nature. These symmetries govern the behavior of reality, even in a completely empty universe. This idea suggests that the transition from nothing to something might not be as extraordinary as it seems, possibly just a shift from one type of nothing to another, an organized void of our universe. Another intriguing question is why black holes are present at the center of nearly every galaxy. With around 2 trillion galaxies in the universe, nearly all contain a supermassive black hole. These black holes range in size from those weighing billions of times the mass of the Sun, like the one in the center of the Milky Way, to smaller ones with masses in the millions of solar masses. How they form is still a great mystery. We know that a black hole can form when a massive star collapses in a supernova explosion, but how the largest black holes form remains unclear. One possible explanation is that they could form in dense star clusters, where black holes collide and merge to form even larger ones. Evidence of this theory comes from the detection of gravitational waves, which were caused by the collision of 2 black holes. Another hypothesis is that very massive black holes could form directly from the collapse of a massive gas cloud. Regardless of the method, these black holes may have formed before the galaxies themselves, providing the necessary seeds for galaxy formation. Supermassive black holes can have a profound effect on the formation of stars, as their jets of energy can either suppress star formation or trigger it, depending on the location in the galaxy. Lastly, dark matter remains one of the most puzzling components of the universe. It doesn't emit or reflect enough light to be detected directly, but its gravitational effects on visible matter reveal its presence. Without dark matter, galaxies like the Milky Way wouldn't have had enough mass to form stars and galaxies as we know them. According to the European Space Agency's Planck satellite, dark matter makes up about 27% of the universe's total mass energy, compared to just 5% for ordinary matter. The leading candidate for dark matter particles is WIMPs, weakly interacting massive particles, but despite their theoretical fit, these particles have yet to be detected.